Hello, everyone. I'm Shitej, co-founder and CTO here at Orb. Today, we're going to be talking about how Orb handles billing for millions of events a second and supports fast-growing companies like Vercel, Replit, and Materialize. This is a story of how we're able to leverage Druid to really scale the platform and to give our customers the insights they need in real time. Let's dive in. Today, I have with me an engineer on our team, Brandon. And so to give you a sense of what we're going to cover today, I'll give you a little bit of product context on Orb, what parts of functionality are powered by Druid, and then Brandon will go into a feature that we're really fond of and worked really hard on, event backfills and correcting usage data once it's already in Orb. To give you a sense of why Orb exists, what we found was that existing billing systems really weren't built for the modern era of pricing. They were often really rigid. They were slow to integrate in that you had to build a bunch of data infrastructure before you could even send data into the billing system. And at the end of the day, they were just slow, sluggish, and inefficient. It meant that your business processes couldn't actually be powered by the billing system, and you had to staff a whole team of billing engineers to architect around it or to build data pipelines in service of your billing system. Now, fundamentally, we think billing systems should be flexible. We think they should be scalable and reliable, and that's how we've built Orb. To give you a sense of what that means, Orb really is the engine that takes usage data as granular as you want and translates it to invoices. It keeps track of that usage data in real time, and those invoices that come out the other end are super detailed, they're really transparent, and they're actionable. So I want to show you how that works in the actual product. Let's dive into an Orb sandbox. Now, typically the place I like to start, which underlies everything in Orb, as well as the data that we store in Druid, are the actual events. So events typically are product usage instrumented in your application coming into Orb. Now, what that means is you shouldn't have to do any pre-transformation or pre-aggregation of your data before it makes it into Orb, and you can do that within the system. So what you're seeing here is the structure of an event. It's pretty simple. It has an idempotency key, a name, a customer identifier, a timestamp, and then a dictionary of properties. These properties typically are some sort of metadata, so labels that will help you identify the context of the event, and then some numeric properties which will actually help you calculate the metric or the aggregate that you're billing. Events come into Orb at an extremely high throughput, so we have customers who are sending us thousands and hundreds of thousands of events a second, whether it's through landing them in a cloud storage bucket or sending them directly to our API. Let's take a look at how you actually take these events, which of course end up in Druid, and build an aggregation on top of them that you can tie to billing. You do that through the concept of billable metrics. Now here's where Orb really starts to look like the marriage between an analytics solution or a BI tool and a billing solution. If we go to create a new metric, of course, we have a drag and drop UI to really quickly preview some events, construct some filters, and specify an aggregation clause. Now, this is interesting, and it actually helps a lot of our customers get off the ground with some basic metrics. But the core insight we had when building Orb was that flexibility is really key. Now, if your go-to-market team comes up with a different way of charging or a different metric that they want to charge, let's say an enterprise customer on, we really don't want Orb to get in the way. And Druid helps us do this really, really well. So in Orb, we actually expose the possibility of just constructing a fully custom SQL query. Now, this lets you express things like subqueries and conditionals and transforms directly within the platform. And what's really powerful about this is you can use all of the properties that you've sent into your events. Of course, in order to do this, we take advantage of some very sophisticated features in Druid. For example, the support for JSON-B columns. Now, Druid lets us execute these queries in a very performant way, But the Orb team has done a bunch of work to make sure that we can translate generic queries written at this layer to queries that are customized to the invoice that we want to calculate, which means parsing the AST of the query and being able to insert in the correct time frame and customer filters. Let's take a look at an example customer and an invoice to see that in action. So here, what we're looking at is a customer called Hyperscale Corp, and they're subscribed to a professional plan. Now, this plan happens to include a few different metrics: API requests, compute, and data ingestion. What you can see here is that we're tracking each of these metrics over the course of the billing period so far, and this data is being refreshed in real time. Whether it's in the web app or in the API, all of this data is as fresh as the events coming into platform and being persisted in Druid. So it's really, really important that we can refresh this data in a matter of seconds. Let's also take a look at the equivalent draft invoice for this current period. As you can see here, the invoice is as transparent as the customer detail page was in the previous view. You can see all of the line items, a breakdown of how we take that usage data and calculate the total line item amount, and then finally a graph of how that usage data has been trending over time. Now, Orb, in addition to this internal view, also has a native invoicing solution. This is really powerful because you can issue these invoices to your customers, and unlike a PDF where you might only have a single quantity, a single rate, and a single total line item amount, Orb's invoices show your end customers just as much transparency as you can see internally. This is really powerful and saves our customers a ton of time, both in dealing with account disputes, as well as just giving their customers a better end user experience. These views need to be backed in real time by a data store like Druid. To give you a sense of Orb's system scale, unlike other billing systems that might restrict you to, say, 50 or 100 requests per second, Orb ingests many billions of events per day and can scale to millions of end customer subscriptions. Now, in order for us to provide the guarantees that we do around freshness and correctness, we need rock-solid data infrastructure underlying that. And that's where Druid and the team at Imply really come in to help us understand our clusters and the axes on which they can scale really well. Another interesting aspect of Orb and the trade-off we've taken around really leaning into flexibility is that our system needs to support both what we call distributive and non-distributive aggregate functions. A distributive aggregate function or query is something like a simple sum or a count. Now, what's interesting about these is they can be calculated in a streaming mode, in the sense that as events are ingested, you can keep a sum or a count up to date pretty easily. Now, on the scaling side, a non-distributive aggregate function like a count distinct is much, much harder. And that's because you can't calculate this in streaming, or at least not with a constant or small size state. Instead, let's say you have a subquery. You often need to scan over the whole data set in order to be able to accurately calculate this query or aggregate, and that's really important for our customers who need that flexibility. So with Druid's ability to scan millions and millions, if not billions of events, that's really important for us to support our customers with the queries that they need. Now, we're really proud to run Druid clusters that serve 1,000+ queries per second, and these help us power workflows like alerting, as well as analytics workflows, both for internal use cases for our customers, as well as to power, in almost all cases, end user-facing dashboards for our customers. I want to talk a little bit about some of the principles we used when architecting Orb with Druid. Now, the first thing, of course, as any user of Druid knows, is that Druid archives its data to deep storage using something like S3. and it replicates data by default across multiple machines. So that element of durability and reliability was extremely important. Now, in terms of correctness, we were able to leverage two key features. One was the inbuilt Kafka ingestion mechanism. Druid doesn't rely on an external Kafka connector. And the second was our use of the indexing and compaction configs to make sure that we never bill for an event twice on an invoice. Working with some of the fastest growing companies, what we've learned is that freshness is critical, even when it comes to billing, which you might think only happens once a month or once a quarter. We use data freshness in Orb to power critical workflows like alerts so that you can alert your internal teams and your end users when you hit a usage or a cost threshold. Finally, Orb is really built to have a predictable and safe developer experience. Using the syntax of SQL powered by Druid lets us pass on not only the flexibility, but that developer experience to our end users, which we think is really important. Now, I want to hand it over to Brandon to talk a little bit about what happens when you send us the wrong data and how you can fix that and how we've architected that on top of Druid.
Hey, I'm Brandon. I'm an engineer at Orb. I'm going to dive into how we help customers correct their usage data. So billing data obviously needs to be accurate, and we put a lot of effort into guaranteeing that usage data we expose is consistent with the events you send us. But what happens when the events we get are wrong? Mistakes happen, and especially at high event volumes, they can be painful to address. In a billing context, these mistakes can seriously affect your business, either through lost revenue or loss of customer trust. This is why we think it's critical that your billing system gives you a way to correct them. To start, let's go through an example. Imagine you're a billing engineer working at FileCo, a large file storage company charging for storage and downloads. Their pricing model is pretty simple: 1 cent per gigabyte downloaded and 2 cents for each terabyte stored each hour. Let's go through what the event reporting pipeline looks like for the gigabytes downloaded price. The metric we're going to evaluate here is pretty simple: just the sum of gigabytes downloaded over the billing period. Now let's look into FileCo's reporting architecture. You have a billing event reporter that tails your request logs, transforming each log entry into a usage event to send to Orb. Each event has the properties Orb needs to compute the amount due each billing period, along with some metadata you may want to expose to your customers, like, for example, the file extension. This pipeline is working fine until FileCo becomes hugely successful, and the event reporter can no longer keep up with the request log throughput. You decide to build a new event reporter that's faster and more scalable. You realize this is a risky change, so you perform a slow rollout. You start by moving a single customer over. So now this single customer is reporting events to the new pipeline. You take a look at the customer's usage data in Orb, but you realize something is very off. Upon debugging a bit, you realize that in the new pipeline, we forgot to scale the bytes to gigabytes. On the bright side, FileCo's revenue just increased by a huge factor, but this customer probably isn't going to be happy to get an invoice for $1 billion. So how do we correct this mistake? We have a few things going for us. We know the time frame of the rollout, so we can say, for example, that only events emitted on October 30th, 2023 were affected. We can produce the correct set of events using the old pipeline. And lastly, we only rolled out the change to a single customer, so we know no other customers were affected. Before we dive into what it'd look like to handle this in Orb, let's talk through what it'd look like to handle this if you were storing this usage data in your own Druid cluster. The steps you take are actually fairly simple. First, you'd re-index the affected day to remove the data from the affected customer. Second, you then ingest the correct set of events for that customer in the affected day. Druid's reindexing works remarkably well, and a solution like this would probably work, but there are two main issues we've seen. The first issue is that the overwrite feature in Druid only supports time bounds. This is fine if you want to replace most of the events in a time range, but it can be really inconvenient if you only want to replace a small subset of events. If you're ingesting billions of usage events each day, and the affected customer only has a few thousand events each day, you'll want to avoid reindexing billions to fix a few thousand. This huge reindexing will not only be slow, but it'll also occupy task slots that might be needed by other critical operations. The second issue is that the effective reindexing is hard to reverse if you make a mistake. You might have noticed that in the previous slide, my customer ID filter was actually wrong. It should have been a not equals, not an equals. The effect of this mistake would have been that usage data for all other customers would have been deleted. It's worth noting that Druid does keep the version of your interval before reindexing, so the old segments are still in your deep storage. But correcting your segments manually is likely not something you want to be doing on your own. Now let's talk about how you'd handle this in the Orb API. Orb's backfill API lets you declare upfront both the time range and scope of the affected events. In this case, we're saying that the events for this customer on October 30th are affected, so we'd like to replace the existing events in that scope. You can then use the regular event ingestion endpoint to send the corrected events in, so you don't need to completely change your event reporting logic in order to perform a backfill. All you need to do is add a backfill ID as a query parameter to your request. Finally, once you're done, you can just close the backfill, telling Orb that all of the corrected events have been ingested. Orb then takes care of updating all caches used for displaying usage data. The biggest benefit to this approach is efficiency. Instead of rewriting the entire day for all customers, which could have contained billions of events, you're just ingesting a small subset of events for the affected customer, which could be in the thousands. This means you can fix your mistake in minutes instead of days. You may even be able to fix the mistake before the affected customer ever sees the incorrect data. The other benefit is that this operation is reversible. I can make a single API call to revert the effects of a backfill. This means that if I accidentally forget to scope the backfill to a single customer, deleting all events for other customers in the day, I can undo it immediately. If I realize the affected time range is actually much narrower than I thought, I can revert the existing backfill and create a new one with a much smaller range. If I accidentally forget to deprecate the existing events, I can revert the backfill to remove any events I incorrectly added. Now I'll dive into how our backfills API is implemented. We generally avoid making any update or delete operations in our Druid cluster. They're just too expensive to expose as user-facing operations. Some of our Druid clusters serve many tenants, so it's not feasible to occupy task slots whenever someone wants to update their data. For example, if we have 500 tenants in a single Druid cluster and only 10 task slots, we likely don't want a single tenant to be using 4. Instead, we tag each event with an optional backfill ID. If you ingest an event as part of a backfill, it gets tagged with the corresponding ID. This allows us to apply the backfill on the query path instead. To illustrate what I mean by applying on the query path, let's use an example. You might remember the billable metric we defined for the gigabytes downloaded price. It's simple, just the sum of downloaded gigabytes. Whenever Orb evaluates this metric to produce an invoice, it also includes additional filters for the customer and time range. This guarantees that we're not billing for events that are outside of the scope of the invoice. This happens for all queries that Orb runs, because we never run queries outside of the context of a customer or time range. Before making this query, we also check to see if there are any backfills affecting the queried customer and time range. If there are, we add an additional filter to account for the backfill. This filter removes any existing events in the time range and includes the events from the backfill. Even if you're writing a more complicated query with subqueries and grouping, which Orb's custom SQL supports, Orb understands the AST and it's able to inject the filter into the right location. As you might imagine, the size of this query can grow pretty large if there are many backfills that affect a single customer. In practice, this hasn't become a problem for us because all billing queries are time-bound. So only the backfills that are incorporated to the query are those that happen during the relevant billing period. This means the size of our queries isn't growing monotonically over time. So if a customer has a few hundred backfills over their lifetime, they may only have a handful within a given month. Finally, if you want to revert the backfill, we simply replace the filter shown on previous slide with a filter removing events associated with the backfill ID. To recap, Orb's backfill API is designed to be efficient and reversible, aiming to simplify the process of correcting usage data. There are clearly other challenges with this implementation that I haven't dug into here, like overlapping backfills and cache invalidation. Feel free to reach out to us if you'd like to learn more.